Chinese scientists have made a significant breakthrough in the world of semiconductors, the South China Morning Post, SCMP, reports. Just one atom thick, thereby termed 2D, the new 12-long, 30.5 cm wafers can be cheaply and potentially revolutionize the semiconductor industry, its creators claim. While more work is needed to turn them into usable microchips, the new wafers could complement, even challenge, traditional silicon chips. Due to its thinness, the new 2D material exhibits superior semiconducting properties. However, the team of scientists faced challenges when it came to scaling up the size of the wafers and producing them in large quantities. We proved to the industry that this is scientifically feasible and instilled confidence. If there are industrial demands in the future, progress in this field will advance by leaps and bounds. Study lead Professor Liu Kaihui of Peking University told SCMP in an exclusive interview. As reported in a study published in Science Bulletin, the new wafers offer some critical improvements over existing silicon chips. When silicon transistors are made thinner, their voltage control becomes worse. Current will exist even when the device is not working. This brings extra energy costs and heat generation, Liu explained. The new 2D material comprises crystalline solids with one or several atom layers. Due to its naturally atomic level thickness, the wafers possess unique physical properties and have potential applications in high-performance electronic devices. A transistor built from a single layer of MOS2, a typical 2D material, with a thickness of about 1 nanometer, outperforms the one made with the same thickness of silicon many times, Liu added. Some 2D materials are considered an essential material system for an integrated circuit of 1 nanometer and smaller. They are also recognized by the industry as being capable of continuing, or even beyond, Moore's law, where the number of transistors in an integrated circuit doubles about every 2 years, he said. However, to date, scientists have struggled to fabricate 2D material wafers with high uniformity and device performance, even though 2D materials can exist separately at each layer. The new wafers can be stacked layer by layer, including materials such as graphene or transition metal dichalcogenides, TMDs, like molybdenum disulfide, tungsten disulfide, molybdenum diselenide, and tungsten diselenide. Mass production close. We developed a new approach, utilizing a surface-to-surface supply method that ensures uniform growth, PhD candidate Shui Guodong, first author of the paper, said. While fabricating the MOS2 wafer, a chalcogenide crystal plate, ZNS, cooperating with solution-dispersed molten salts, sodium orthomolybdate, is used as an element source, Guodong added. Our engineering team at Songshan Lake Materials Laboratory designed equipment based on this method. Our equipment can now produce 10,000 pieces of 2D wafers per machine per year, Liu said. Two-dimensional, 2D, transition metal dichalcogenides, TMDs, are regarded as pivotal semiconductor candidates for next-generation devices due to their atomic scale thickness, high carrier mobility, and ultra-fast charge transfer. In analog to the traditional semiconductor industry, batch production of wafer-scale TMDs is the prerequisite to proceeding with their integrated circuits evolution. However, the production capacity of TMD wafers is typically constrained to a single and small piece per batch, mainly ranging from 2 to 4 inches, due to the stringent conditions required for effective mass transport of multiple precursors during growth. Here we developed a modularized growth strategy for batch production of wafer-scale TMDs, enabling the fabrication of 2-inch wafers, 15 pieces per batch, up to a record large size of 12-inch wafers, 3 pieces per batch. Each module, comprising a self-sufficient local precursor supply unit for robust individual TMD wafer growth, is vertically stacked with others to form an integrated array and thus a batch growth. Comprehensive characterization techniques, including optical spectroscopy, electron microscopy, and transport measurements unambiguously illustrate the high crystallinity and the large area uniformity of as-prepared monolayer films. Furthermore, these modularized units demonstrate versatility by enabling the conversion of as-produced wafer-scale MOS2 into various structures, such as Janus structures of MOS, alloy compounds of MOS2, 1-X, Say2X, and in plane heterostructures of MOS2. This methodology showcases high-quality and high-yield wafer output and potentially enables the seamless transition from lab-scale to industrial-scale 2D semiconductor complementary to silicon technology.